Gitiaux. He's our graduate student from CS department, and is working with me on the quantum computing problem estimation of overlap among the arbitrary number of quantum states. If you're ready, Javier, please go ahead. Thank you.
Hey, good morning, everyone. My name is Xavier Gitiaux. As Frank just said, I'm a CS PhD student. And the project I'm going to talk is actually interdisciplinary, which is good because quantum computing is interdisciplinary. Can come to speak to this today because Yan and Ming from the physics department and Maria, which I don't think is here today, is from the math department. So interdisciplinary project, and the goal is to solve what looked like a very simple problem, but on a quantum machine that make it a little bit harder and interesting. So I'm going to convince you it's not so easy, and I'm going to convince you it's an interesting problem. And the idea is, again, simple. You give me m vector, phi1, phi m, and I want to compute the so-called overlap, which is the square of the inner product between phi I and phi j for all possible pairs ij in the set 1 to n. So a fairly simple question to start with. And so the goal is to compute this and compute this on the quantum machine. And what would we care? We care for many reasons. In fact, I came to this question from my perspective, which is machine learning originally, because if you think that phi1, phi m are classical vectors, then that's really a primitive. That's one of the biggest primitive in machine learning. Maybe actually machine learning maybe a lot about computing these overlaps. You could note, for example, very simple math that if all the vectors are real this time, in classical vectors, looking at the difference in distance, the distance is actually relates to the inner product between phi I and phi j. But further than that, one simple idea in machine learning is the left problem. So you look on the left side of this graph, you have some data, and you have some red and some blue, and the goal is to try to find a simple line that will separate the red from the blue. Clearly on the left, you cannot do that because you need to draw a circle really. And so if you just look at the line, that's never going to separate fully the blue and the red. But what a lot of machine learning is about is to take this data and map it to another space where they will actually neatly separate, like the space on the right, and you can just, it's easy to find a hyperplan that will separate the blue and the left points. And the machinery that sends you from the left to the right is so-called a kernel, and so many of the kernel are computed by taking vectors and just looking at the overlap between these vectors, or function of the overlap. It doesn't have to be as simple as the one I wrote here, but function of this overlap would form a kernel, and this kernel would be very useful to map the data that's on the left to the right. So a very classical thing to do in machine learning. And the question, obviously, for people who would like to do machine learning on the quantum machine, we need to do this on a quantum machine. Another example of why in the classical world in matter of lot, it's nearest neighbor classification. Same thing, you have a ton of points here. There is a green or they are red. And the goal now, you get the point that's in the middle with the purple arrow. And you want is it going to be a green? So let's say you don't know yet the color, and you want is it to be a green or is it going to be a red? Well, what you do is you draw a circle of some radius and take all the points that are within the circle and look, are they in majority green or in majority red? If they are green, you say the point in the middle is going to be green. If the majority is red, you say the target point is going to be red. And here it turns out that you have 1, 2, 3 green, and you only have 2 red. So you say, well, that's a green. And the reason why go back to what we want to do. To compute that circle, you need some notion of distance, and to compute that distance, you're going to need some notion of overlap, or the inner product between each of these points. So again, the classical thing to do, but computing overlap is not just about doing stuff on the quantum machine that we know how to do on the classical machine, and hopefully faster. The goal is also, there are things that we want to do that are just quantum. It could just be things that are just quantum and that not necessarily have classical counterpart. So beside just doing quantum-based machine learning. And here are a few examples, probably more, but here are the few ones we have thought about. One simple is you give me m quantum vector, and you ask me which one are the, I don't know them, I don't know how they were produced. They are produced by some polynomial size circuits or something else, but I just want to know which one of those are identical. So to do this, I could compute or which one are have a high overlap, almost identical, if not perfectly. And to do this, I could compute the overlap, the square root of the inner product, then look at the one for which this overlap is high. And there was a few papers that attempt to do that. There is also this idea of dimension widthness. You give me m quantum vector, and I want to know what is the dimension of the space they span, because obviously it doesn't have to be of dimension n, it could be much smaller than that. And I would like to know what the smaller number is. And that's actually not a trivial thing to do. And to do that, you also can use the overlap between these vectors. There was a paper that gives some theory about this. There is also this idea of coherence widthness, and let me show you an example of how that looks like. And I make really nicely the difference between what's called classical and quantum vectors. So let's say you take three vectors, you know, and all normalized, and on the right, you plot all the possible overlaps, all the possible square inner product between these three vectors. So that creates a convex hull of possible values that is plotted here, like this 3D object. That's what the classical vector would give you. Now, if you do the same with a quantum vector, that's the left, and you see, it's not so clear, but it's kind of clear. You see that it's a little bit bigger, it's a little bit fatter on some parts, it's a bit rounder, and it does encompass the one on the right, but it's a little bit bigger. So there is a piece of this shape on the left that represent what's called, so all the one on the right are coherence-free vectors, and the one on the left, the one that are not into comprehend in the one on the right, are actually the one that show coherence. And so we can say that looking at these points that are in the part that is quantum but not classical, give us a test for whether you look at coherent-free or not vector. So those are ideas of what you would care about computing overlap. You could use overlap to have a test on whether you are coherent-free or not. So, and that was an idea of a paper of Ernesto Galvao and Broad, 2020. And so the issue, and that's where our project is the issue is that most of the current state of the art in that area doesn't know how to compute many overlaps. In fact, the current state of the art is not totally true, but let's say the most basic stuff we know how to do is to just compute two, phi one. So I can only do with m equal 2. I can only take two vectors and compute the overlap, and that's it. And to do this, we do have a circuit to do that. That's fairly simple. It's actually not so simple. It's actually not simple at all. But so you take these two vector phi, quantum vector phi 1, phi 2. You put them on a wire. You add what's so-called an on-series, which is, you know, an additional auxiliary wire that's going to help you. And and you pass this, you set this ancillary to a quantum state 0. And mostly the idea of what you're going to do is you're going to swap phi1, phi2, controlled by the top auxiliary wire. And by control, it means that when the wire is going to be 0, you don't do the swap. And when the wire is going to be 1, you are going to do the swap. And then you're going to eventually do a measurement on the top wire to look at an outcome. And it turns out that, that when you do the measurement on this top wire, you're going to see two things: either it's a 0 or either it's a 1. And it turned out that the probability that a 0 relates nicely to the inner product between phi1 and phi2. In fact, it's 1 plus the square of the plus the overlap divided by 2. And so we do a simple test when we only have two vectors. We just built this test with this gate that's called a control swap gate because it's controlled by an auxiliary wire, and then with the measurement on the top. So one measurement on the top wire, and the probability to observe a 1 relates nicely to the inner product. The issue is that that's only for m equal 2. What I want to do is inner product between m and m could be anything. It could be 2, it could be 3, 4, 5, it could be anything. And so the question is, can we build a circuit that will be equivalent to that and that will deliver me not just phi1, phi2, but phi1, phi2, phi1, phi3, and so on for the m times n minus 1 divided by 2 pairs. Now, before we follow, we look at this question that the circuit that I show you actually had a photon equivalent. You could build the same type of circuit using beamers and photonic circuits, and you would get exactly the same measurement, except that instead of doing using a chip, now you would use a detector. Now this D1 here on this photon circuit will play exactly the same role as measurement that was on the quantum circuit. So there is some equivalent with other type of approach also. And that has been used to measure photon indistinguishability, whether two photons are in the same state or not. But to come back to our question, all these tests right now only do m equal 2, and the only way I could do all the pairs would be to repeat the test. So I would have to do, build a circuit for many pairs. So build a circuit for phi1, phi2, then build a circuit for phi1, phi3, and such and such. So I would have to repeat the operation. So the circuits. And the issue with that, well, first of all, that's going to be a lot of circuits because there's m n minus 1 divided by 2 pairs. So a lot of tests to repeat. And the second problem is that it's actually you cannot hope that once I have done phi1, phi2, I can still use the same phi1 so to actually do phi1, phi3. It's unfortunate, but on the outset of my my control swap gate, the phi1, phi2 are untangled, and so that I cannot recover phi1 or phi2 and use it to now compute the inner product with phi3. So because of entanglement, once I've done my control swap, that's done. I cannot reuse phi1, neither phi2 to compute another inner product. So which means I need a new copy of the state. To compute phi1, phi3, I'm going to need a new copy of the state. There is nothing else I can do. So it could be very quickly wasteful. If phi1, phi-m are states, quantum states that have been created by complicating circuits, and I even don't know, it's going to be wasteful if after I compute phi1, phi2, I have to get another copy to compute phi1, phi3. So the question we ask ourselves is, can we just do all of them in once? And can we build a circuit for which we do all of them in once? There's a little bit of a caveat here. The answer, because you have to also put some constraint on this question, otherwise it's not so useful. And especially you have to put some constraint on how much measurement you are going to make. Remember, in the original swap test, we did one measurement, which is good because it's only one. Measurements are expensive. If I'm having to do n measurement, then the probability is going to scale as 1 over 2 to the n, which means they're going to be very tiny. And to see events happening on all the outcome from all the detectors, the n detectors, I'm going to have to repeat again the test many times, and that's going to be wasteful as well. So if I want to do this without repeating over and over the test, or with repeating with only a constrained amount of copies, I'm going to have to constrain the amount of measurement. And especially, we're going to try to use a measurement that is logarithm of the number of vectors, which will mean if this is in the order of a logarithm, it means that the probability will scale as 1 over m, which is much better than, for example, if I were using m measurement, I will scale as 1 over 2 to the m, which is a very tiny number, and I will need an order of magnitude 2 to the m measurements, which is a lot and could be too much. So the way we went about that is actually a fairly simple, end up being a fairly simple approach. We did something where we say, I'm going to do two things. First, I am going to take these m, I'm going to show you how in a minute, these m vectors, and I'm going to make sure I create a state such that I know for sure that each pair of vector appears in the two top wire of the circuits. And then I will just do a simple swap. I would just add a simple control swap gate as the one I showed you before. More precisely, what's going to happen here is the circuit we're going to use. So what happens is you have these vector phi1, phi2, etc., to phi n. And the idea is I'm going to create a machinery first. And this machinery, what it's going to do is going to bring all the vector phi 3 to phi m on the top two registers, so that we know after we use this machinery m with unitary m, we call this pair unitary m, that if I look at the top two wire, I'm sure to see all the pairs phi I, phi j. There is a state where the pair phi I, phi j is going to show up. And then I'm just going to do one more control swaps, which I describe here, and do measurement on the top auxiliaries. So how many auxiliaries can I use? Again, I am limited in the number of measurements I can make. So I am actually limited in the number of auxiliaries on series wire I can use, and I'm going to use log n. It means that dn has to be of the order of magnitude log n. And now most of the, so it's actually very easy to see that if UM works, meaning if UM can create a state where each pair can appear in the top two wire of the circuits, if there is a state where each pair can appear on the top two wire of the circuit, then when I do measurement, the probability of observing, I can link the measurement to the overlaps exactly as we saw it before with the two qubit simple qubit swap test. So the only issue is to make sure that we can build actually a unitary that does UN, that does what we want it to do. And we show we can, and we actually have with only, by the way, with only log m, or an order of magnitude log m on series. And what we show is actually we can. So here is the, by the way, here is the unitary. So the unitary is written in the circuit format, and it's what it really does. Again, this unitary UM takes some auxiliary wires and the m vector quantum states, and just untangle them such that for each pair now. I can see each pair on the top two wires, the two first position of the vectors. given an index ij. And so how do we build UM? We actually did something, this is very computer science kind of thing. We did a kind of a divide and conquest approach or recursive approach where we say, well, if I knew how to do UM for anything smaller, for any M prime smaller than M, I will know how to do it for UM. And the idea is that you can actually, you don't just have to use, so here you would do U for the floor of M over 2, and then you will apply it to the top phi 1 phi M over 2. Then you will apply U to the ceiling of M over 2 for the remaining vectors. Note that you can actually make them just use the same on series so far. So they can share the same on series. And then you only have to add 3 control swap gates, and that will get you a circuit such that all pairs appear in the top 2 registers, the top 2 wire phi here, the one where phi 1 and phi 2 was used as input originally. So it's a recursive approach. The last thing we have to show that's, so you have to think when you do the recursive approach. One is to show that if I have a circuit for M prime smaller than M, I can construct UM. The second thing I have to show that I also have a base case. I have a small circuit that can work. And here we show, for example, how we can build U4. I may not go immerse a lot in the detail of what's happening here, but here is a circuit that can make sure that on this outset, I will see a state where all the pair between phi 1, phi 2, phi 3, phi 4 will show up on the top 2 wires. And this circuit is using 3 control swap gates and 3 on series. And I show you a little bit the math here, and you can check that. So I have, let's say in state 0, 0, 0, I would get on the top, so if I go and measure these 2 wires, I would get phi 1, phi 2. But now if I look at 0, 0, 1, I would get the pair phi 3, phi 2. And if I look at another state, you can show, for example, 1, 1, 1. In this state, you would show that, so when the on series here are 1, 1, 1, you know that the pair you measure on the top 2 register is going to be phi 4, phi 1. And you can check, you get all of them. In fact, you get a little bit more because a couple of them are appearing twice. But that's fine. As long as you have them once, it's fine. It serves the purpose of it. And in terms of size, so we show that we need 3 times log m on series. Remember, I told you that we want some sort of order of magnitude log m. So we are there here. We can use only 3 times log m on series. On the other end, we use a linear amount of control swap gates to do it. In fact, we found the exact number is 3m over 2 minus a small constant to be precise. And so for us now, the question is, before the question, here is the overall. So this circuit I'm drawing here with the unitary and the control swap on the outset. That's going to compute you all. So when you do the measurement here on these on series wires, you will be able to link back to the overlap between phi I, phi j for all pair I and j, and all of this using only an order of magnitude log m measurements and a linear amount of control swap gates. And that's why we formalize a little bit further in this result. That's the main, so far, this is the main result we have in this project. And I think it's quite already a result because no one has done it for an arbitrary m. Most of the current state is between m equals 2 and m equals 3. So we show we can actually do it for any m and without blowing up the number of measurement. The question we have now is multiple. One is how optimal is a circuit? So, and obviously the question is tricky because how do you find optimality is a little bit tricky here. Not that we know already that we need some sort of order of magnitude log m on series. And the reason is that you have m minus 1 over 2 pairs. So somehow you're going to need log m minus 1/2 ancillaries to encode these pairs and to like index these pairs in some ways. And so, which is about 2 log m in order of magnitude. So in some way, 3 log m, which is what we get right now, is actually not so bad. It's actually optimal up to a constant. Obviously, the question is, does there exist a circuit that would use only 2 log m on series? We have not answered that question. And we have not answered that question. The second question we have is, well, now we use 3/2 control swap gates. And we don't know if for circuits that use log m or order of log m on series measurement, we can actually get fewer control swap gates. And I'm telling you this because it turned out, and that's something, and I will finish on this point, it's actually an important problem. Control swap gates are actually not so simple. They're actually very complex. If I were extending them in the full format, as it was shown in the previous presentation for other type of unitary, it's a very deep computation. I think it requires 8 or 9 gates to actually Ming will tell you better than this, to actually like universal gates to actually compute this control swap gates. And we found empirically that 1 works well, 2 gets tricky, and we have not been able. We're working right now on a real machine for m control swap gates, and yet we have not yet been able to make it work. So also we have a result for any m. We are right now working on a much smaller number of vectors because it's tricky to implement. And what do we plan to do later on? Implement on the machine, find the machine that can actually handle even small number like m equal 4, and do some application to that type of method. So that's all I have for you.